So let me give a few words of introduction. So I am Clément Moore, and I'm introducing Jacob, that I actually have known for almost a decade, I think. So it's really a pleasure to introduce him. I think we first met, I don't know if it's 2012 or 13, but anyway, around that time.
Yeah.
And so a person I've talked math with a lot, collaborated on several papers, and so it's really a pleasure. So Jacob got his PhD at UCLA. I think the advisor was Bertozzi, right? Andrea Bertozzi, I think.
Yeah, there was also a second advisor, Joseph Turan.
Yeah, that's what I was not totally sure about. I looked at your PhD, there was several names, but that's the name I remembered. And yeah, a PhD is significantly less, let's say, more geared towards modeling and numerics than what you did afterwards. I mean,
yeah.
So there's a wide spectrum here. Then he did a postdoc with Nader Masmoudi at the Courant Institute in New York. After UCLA moved to Courant Institute, and then moved to Maryland where he became assistant professor, associate, and full professor very young, 2019. He got actually a lot of prizes in just a few years, following a huge series of papers since 2012-13. So just to mention a few: Sloan Fellowship, IMA Prize, the SIAM APDE Prize, the Peter Lax Award, which is a new award, I think created when Jacob was awarded the award. And he was an invited speaker at the last ICM in 22. So I'm stopping here for the few words of introduction, and it's a pleasure to have Jacob presenting a talk on Landau damping and related effects in kinetic models of plasma physics, an overview of the mathematical progress. Please, Jacob.
Okay, thanks a lot for the very nice introduction. It's really nice to be here. Okay, so let me just take it away, I guess. Okay, so I'm talking about, it's an overview talk. I will have to skip some things. The field is now so big that it's hard to overview everything in one single talk. So I'll overview certain aspects and just mention the existence of some other aspects. So I'm talking about the kinetic theory of plasmas, and the general sort of high-level overview kind of models. They all basically look like this. So you have a set of species. So plasmas generally contain electrons and at least one type of ion. And real plasmas contain a whole list of other things like neutrons flying around and stuff like that. And for each species, you have a distribution function, which is going to be a function of t, x, and v. Okay, so it's like 7 variables. And what it basically tells you is it tells you roughly speaking, it tells you the number of particles at location x moving with velocity v. So unlike a fluid mechanics model or a continuum mechanics model, you are not assuming that the particles are in local thermodynamic equilibrium. So you could have beams of particles moving through one another that are moving at completely different velocities. So at every location in space, you no longer have a notion of specific velocity at that one point. All the particles moving in a distribution. And the physical effects are as follows. So this term just tells you that particles with velocity v move through space with that velocity. So it's a transport term. Very simple to interpret. This is an acceleration term. That's why you have a sort of transport in velocity direction, dot grad v. And this force is the Lorentz force. So it's what a charged particle will feel moving through an electromagnetic field. And then the diciest part of kinetic plasma modeling are these so-called collision operators, which basically account for the near collisions of different types of species. So electrons can collide with electrons, but they can also collide with all the different types of ions and vice versa. So that you actually can have a plethora of different collision operators. I will mostly not be talking about collisions today. I kind of cut that from the talk, but they are important in plasmas. And one of the cases that comes up a lot in plasmas are, for example, when these collision frequencies, these kappas, are very small. And when these collision frequencies are very small, then you're going to be far from local thermodynamic equilibrium. So if these things are big, then you can be close to thermodynamic equilibrium, and maybe you don't need kinetic theory. You can use macroscopic models like Euler-Maxwell or magnetohydrodynamics or something like that. Normally, this is kind of unwieldy to study this huge system, especially when you have cross collisions. And so normally we reduce our consideration to thinking about one species at a time. I'll talk a little bit about multi-species models. Actually, for most of what I'm talking about, the extension is actually straightforward to at least 2 species. So you have one distribution. So either you're looking at the electrons or the ions. These 2 different species tend to evolve on very different timescales because electrons are a couple of 1,000 times lighter than ions. And so you can focus on one or the other and kind of idealize away the other species. The simplest model, simple in some sense anyway, are the collisionless Vlasov equations. It's a beautiful, beautiful model. So in this setting, there's no magnetic field effects and there's no collisions. And so all you have is the electric field. And here we're taking the electric field to be self-generated by the plasma. So there's 2 things coming here. So there's this rho bar, which is the density. So this is kind of, that's the number of particles at a location x, irrespective of how fast they're moving. So you just integrate in the v variable. So it's a marginal distribution function. This rho naught is the background charge density. And you need that, right? Because plasmas are pretty much charge neutral. It's just that the charges are not all evenly distributed. So if you're looking at the electrons, the ions are still there, and you're going to see them with a constant ion background rho naught, at least in this simple setting. And so if you're modeling the electrons, then you just have standard electrostatic interactions, just like in Maxwell equations, but with the electrostatic restriction. So this W hat, this interaction kernel, will be like 1 over Laplacian. If you're looking at the ions, and actually that's not really what you get. So what you should get is that the electrons should instantly equilibrate, and they should sort of conspire to shield the long range effect of the electric field. So you have this shielding here. So it's like you have a lower order term in Poisson equation, which screens the low frequencies. If you have no low frequencies in the system, if you're thinking about the torus, it doesn't make a big difference, the screening or unscreening, but as we'll see on the whole space, it makes a huge difference. So the ions and the electrons behave totally differently in the Vlasov equations, at least at large waves. You can actually use this model also with the other sign. So instead of electrostatic interactions, you're looking at gravitational interactions. This is actually a pretty interesting and good model for certain types of celestial dynamics. So you're looking at like stars in a galaxy. You would think that you would always have to use Einstein gravitation, but actually that's not quite true. So there are some cases where you can use Newtonian gravitation to get the more or less the right answer. One thing that the math community hasn't really delved into too deeply yet is that most real plasmas are subjected to large magnetic fields. Both certainly in the laboratory, if we're trying to build a fusion reactor, they have huge magnetic fields in tokamaks, but also even in astrophysical plasmas like the ionosphere and a solar wind, they're all dictated by large magnetic fields. But we don't, I'll talk a little bit about that at the end, but probably not. I'll surely run out of time. Okay, so for the Vlasov equations, well, the Vlasov equations, one thing that's not on the slides is they're like the only really equation of sort of continuum mechanics. It's not really continuum mechanics, but basically mesoscale mechanics or macroscale mechanics, which is globally well posed for smooth solutions in 3D. Just a nice side, just a side comment. The Vlasov equations are especially beautiful. Okay, so any homogeneous distribution, F naught is an equilibrium. So that's where the electrons are just spread out evenly in the plasma. So you want to ask, well, how stable is this equilibrium? So then you linearize the equation. So you take H, a perturbation, and you make this linearization. So it's a simple linearization. You have this relatively compact perturbation, so compact relative to this v dot right x. And so it's a pretty nice equation. So let's think about it on the periodic box. So a simple case where the x waves are kind of bounded in wavelength. So what Landau showed is that if you take a Maxwellian distribution, so you take thermodynamic equilibrium, which is the most natural steady state to study, but not the only interesting one, because again, in the kinetic theory, you don't need to be near thermodynamic equilibrium. And he showed that if the initial perturbation is analytic, then the density of the perturbation, this rho here, decays exponentially fast. So it decays, it looks like sort of square root heat equation. So it looks like the square root heat equation kind of decay. That's really fast, and it's interesting because this equation is time reversible. So you're getting decay in a time reversible equation. So you know, of course, the equation is time reversible, so you know that it's not actually nothing like the heat equation. So you should think of it as more like dispersive decay. So dispersive equations can decay if you measure the right norms, even though they are time reversible. And that's the analogy that you should be keeping in mind with this effect. It is related to regularity, as we'll see on the next slide. So if you're not analytic, then your decay is not exponential. Your decay is you get about 1 over kt, where k is the wave number for every frequency. Sorry, for every derivative that you have. So this effect is what's called Landau damping, and it's considered very important in the kinetic theory of plasma. So when the plasma is weakly collisional, it's a really important effect. Okay, let's talk about what is it. So just, I mean, if you think about it, this is a relatively compact perturbation. So if you think from a spectral theory perspective, the spectrum is all dictated by, well, not really. If you rule out neutral modes and unstable eigenvalues, the essential spectrum is dictated by this piece. And we'll see the essential spectrum is what generates everything. So let's just think about the kinetic free transport equation. So this just says the electrons move at constant velocity. This you can solve. You just write down the solution, very simple. And here I've drawn a picture if you have velocity and x. This is what it looks like. So these fast particles go faster, and then they start lapping the slow particles, and it winds up in xv space. So it winds up in phase space. So it stirs up like mixing milk into coffee in phase space. So hence why this is called phase mixing. And it's useful to think both in physical and Fourier. So up to factors of 2 pi, which I don't care about. The Fourier transform of the density is the Fourier transform of the initial condition at x wave number k and v wave number kt. So that's the v wave number. And then you can see from that Fourier transform formula that you're going to get decay if you have regularity. And you can relatively easily derive these 2 types of Landau damping estimates on the kinetic free transport equation. So for example, the simple one, I guess, is the simplest one is actually the latter. We use the L infinity norm of the density, sort of kt to the beta power is controlled by this norm. And so you can see that sort of this hallmark of Landau damping is this kt. So every derivative gains you a power of time, so to speak. Yeah, and then this you have this other kind of L2 in time h.1/2 space. So you gain half a derivative for free. It's like velocity averaging. And Landau damping is basically velocity averaging with a twist. And when you learn about this stuff, you open a physics book, you'll hear all sorts of weird stuff about particles surfing on waves. And when I first learned it, I was just like, "What are you guys talking about? I don't care. This is very simple mixing effect. I don't need to hear about wave particle resonances." Well, we'll see. The wave particle resonance is actually important, but on R3, on the torus, you don't actually need it to understand what's happening. So how does Landau prove his theorem, or what is a modern proof of Landau's theorem? So let's take the Fourier transform in just x variables, and you have this linear system. And what's nice about this linear system is that you can integrate this away using an integrating factor, and then when you integrate in time and velocity, you get this formula. So I skipped a few steps, but let's just look at the formula. This is the density from free. This is the same density that you would get in free transport. I'm going to denote that S. And in general, if you have the nonlinearity, if you have other sources here, then they will appear here. And then you have this linear interaction term that comes from here. And what you have is the density again, rho at t tau k, with this kernel. So it's some interaction kernel evaluated at t minus tau. So this is a Voltaire equation. So it's basically an ODE. It's a sort of slight generalization of an ODE. And so Voltaire equations, the classical method for solving Voltaire equations is with a Laplace transform. So if you Laplace transform the equation, the time convolution just becomes multiplication, and you have this formula. And so of course, you can invert, you can solve for rho tilde, the Laplace transform of rho, if 1 minus k is away from 0. So the poles of 1 minus k, or sorry, the zeros of 1 minus k, or the poles of 1 minus k inverse, are kind of where you could potentially have problems, in theory. And if you can solve for the Laplace transform of rho tilde, then you just invert the Laplace transform with this formula, which involves integrating. So if we draw the complex plane here, involves integrating on a contour like this. Okay, I always mess up which direction it goes, but it's fine. It's not such a big deal. a priori, you have to put that contour all the way over somewhere on the right half plane. But if you want to see decay estimates, you want to be able to push that contour over to the left half plane. And so there's a very simple stability condition called the Penrose stability condition, which is the requirement that this K stays away from 1 sort of in a suitable right half plane. So if you basically that you can solve rho tilde was S divided by 1 minus K, and that this thing can be extended as an analytic function in some right half plane that is on the other side of the imaginary axis. And if you can do that, then you can use classical Voltaire equation theory, like from the 1930s, and you can write down the solution. You can just write down the solution operator in terms of some kernel R, which has to do with the inverse Laplace transform of your K, the interaction K. And then what you have to do from there is you want to prove that this R has good decay estimates. Once you have something like that, then you can prove pretty directly that whatever Landau damping estimates you have on S, rho will have the same Landau damping estimates. So that's how you lift the Landau damping estimates for the free transport to the Landau damping estimates on the real linearized Vlasov-Poisson equation by estimating this capital R. This is not exactly what Landau did, but it's pretty much what Landau did. And one thing you can also do is, of course, this electric field, once you know Landau damping, this electric field is decaying really fast. And so the solution to the linearized Vlasov equation will basically converge to a solution of the free transport equation, which makes sense. I mean, the forces are vanishing, so of course all the electrons are going to be following ballistic free transport for a long time, as time goes to infinity. This calculus is very easy to extend to at least 2 species. It doesn't really change anything except you have a system that you have to invert, and the Penrose stability condition is basically the same with some small variations. So you can do definitely 2 species really easy. I'm sure that n species is pretty easy if you were less lazy. Okay, what happens on R3? Here, things actually are different. So let's talk first about the screening case. So if you have screening, so now we're talking about ions, then what happens is basically a very sort of enhancement of the calculation that we did on the previous slide does extend onto R3 or Rn, at least n bigger than or equal to 2 for the screened Vlasov-Poisson. So it's not Vlasov, it's not Poisson, it's screened Poisson. And roughly speaking, you can prove the same Landau damping estimates. Now, you have an element of dispersion, so the solution is kind of spreading out on R3, not just kind of stirring in on itself on the torus. So it is a little different, and so in particular, you're going to get very different answers depending on what LP space that you measure the electric field in, for example. And I would say the fundamental estimate that you want to see is this one. So you see a kind of L infinity decay estimate of the electric field. That's like 1/t to the 4th power. That's pretty fast, actually. This is in 3D. And you still see sort of the characteristic KT to the beta Landau damping. So every K derivative gains you a power of time decay. This argument is also easy to extend to multiple species of ions. So you can't just add electrons to this model. It doesn't make sense. Well, not unfortunately, just it is the fact that on R3, the electrons behave totally different. Well, I mean, yeah, pretty much totally differently. And this was actually pointed out essentially by Landau or even by Vlasov in the 1930s. I would say Vlasov was the one who really pointed it out. And then Landau pointed out more. And the Glassy and Schaefer have a mathematic rigorous study that really shows that, yeah, Landau damping, this Landau damping completely fails for the electrons on Earth and in RD. So you basically have no Landau damping. If you just ask how fast is the electric field decay, the answer is almost nothing. In L2, for example, the electric field basically doesn't decay in L2. What you can do is the following. So there's independent works that came out about the same time. I think they were like a couple of weeks earlier than us. I'll state the version that we have. And so basically what you can say is that you can decompose the electric field into 2 pieces, a piece that I'm going to call Klein-Gordon, and for reasons which will become clear, and then a piece which I'm going to call Landau damping. And the piece that I'm going to call Landau damping does have the same estimates, actually, that the screened Vlasov case, which is fast. So it has the same decay estimate as this. That's fast, and I'll explain in a couple slides. It's actually faster than you think that should be possible, or than what we thought should be possible. So this, yeah. But the Klein-Gordon piece basically doesn't decay at all, more or less. So the Klein-Gordon piece is it's sort of only happening at low frequencies in X. And you can actually asymptotically expansion, like if you expand in a power series in K, in like low wave numbers, you can actually get, you get an reasonably explicit power series, but I just wrote down the first 2 terms. So there's some oscillatory phase omega k. There's a damping lambda of k. And if you look at this, this looks like the wave equation, basically, right? It looks like partial tt equals omega of gradient applied to omega squared gradient applied to u. So it's like a slight generalization of the wave equation. And so what's happening? So what's happening is that 1 minus k inverse has a pair of poles. So, and these poles are really close to the imaginary axis. So here's the imaginary axis here, and there's poles right here, which are, and you can come up with an asymptotic expansion for the poles, at least, well, you can come up with the asymptotic expansion for the imaginary part of the poles explicitly. If you put in all the physical parameters and keep track of everything like you're a physicist, then you can actually show that omega squared is actually exactly this omega p squared, which is called the plasma frequency, so the most fundamental frequency in plasma physics, plus this correction k squared plus higher order correction. So you have like a order k to the fourth correction. That was supposed to be a k. That does nothing look like, looks nothing like a k. The Landau damping rate is really, really small. So it's super small, just completely irrelevant, basically. As you'll see on the next slide, it's actually kind of like exponentially small in k. So lambda is like e to the minus 1 over k squared, basically. It's kind of irrelevantly weak Landau damping. And so how you want to study this, you want to say, well, I have sort of nice poles. So I have that my inverse Laplace transform, or I have that my Laplace transform is meromorphic in a nice right half plane. And so I want to punch the poles out with a keyhole contour. And that's going to give me my Klein-Gordon part of the electric field. So why Klein-Gordon? Well, this is the dispersion relation of Klein-Gordon with the fundamental frequency omega p. And so these two poles should give me the Klein-Gordon piece, and the Landau damping piece should come from the integral along the rest of the contour. That's actually a slight oversimplification, which I won't get too into, but let's do a few comments. So first of all, this dispersion relation here, the reason I put in the physical constants is to emphasize that this is the exact dispersion relation that you get exactly when you linearize the Euler-Poisson equations around a homogeneous equilibrium. So it's not just any kind of Klein-Gordon equation. It's actually the exact Klein-Gordon equation that you get if you look at the macroscopic fluid model for the plasma, which is interesting because you're not in thermodynamic equilibrium. So this isn't a collisional limit where you should be getting the hydrodynamic equations as a limit of the kinetic equations. That's not what's happening. It's somehow you're looking at such macroscopic scales compared to the particles that it still looks like a fluid in a sense. It still looks like the Euler equations. This is just a linearized sort of compressible Euler-Poisson equations around a homogeneous equilibrium. These waves are actually the most fundamental waves in plasma. They're called Langmuir waves, are just sometimes just called electron plasma oscillations. And okay, so our paper, we didn't get the exact decay rate, but talking with Benoit Pauseter and then, so Benoit knows how to get the exact decay rate. You just have to throw in a little bit of extra complex analysis than we used. You just have to be more clever with your complex analysis, and you can get that the decay rate is really this, which is ridiculously weak. This dispersion relation was actually predicted first by Vlasov in the 1930s. And he just didn't realize that it should be sort of super weakly damped. And he didn't know about the rest of the electric field. He was just looking for kind of neutral modes. And he sort of found these approximate neutral modes. And he was right. They are approximately neutral modes. I mean, the Landau damping is so weak that it's kind of irrelevant, I would argue. Now, to get the Landau damping part of the electric field is a little bit trickier. So what you actually have to do is you have to integrate by parts in time. So once you punch out the poles, you get oscillating factors. You get sort of like time integrals of oscillations. And it turns out that you need to integrate those by parts in time in order to really see what's going on. So it's equivalent to a normal form transform of sorts. So you integrate by parts in time, actually a few times if you want to get the right, really correct asymptotics. And then that plus you have to deal with this contour integral on this contour, and in order to get the really good estimates to show that the electric field is really like 1 over t to the 4th instead of 1 over t squared, which would be the obvious guess, you have to sort of bend the contour in a specific way and do some detailed analysis. So basically what you can prove is that after you've removed the poles from the density, the remaining density has an order k squared gain at low frequencies. So that way, when you look at the electric field, right, this is what the electric field looks like. It's no longer, it no longer looks like this, like it would for free transport, right? So for free transport, actually the decay of the electric field would be like 1/t squared if you have no screening. But that's not what happens here, because really what we're going to see is something that looks more like this, which now will decay like 1/t to the 4th. And so there's actually a sort of subtle gain there. One last thing I want to talk about in terms of this this kind of like extracting these waves is that here exactly is where the wave particle resonance thing is happening. So in order for, so at the macroscopic scales, we don't see the individual particles, but we do see the macroscopic plasma waves. So we see these Langmuir waves moving through the plasma. And the thing is, in order for a particle to be resonant with the wave, and in order to have some non-trivial energy transfer between the wave, the energy in the wave, and energy in the particles, so the kinetic energy of the sort of kinetic energy in the microscopic part of the plasma, in order for there to be some non-trivial interaction, the particles need to be resonant with the wave. And for a particle to be resonant with a Langmuir wave, it needs to have k dot v equals approximately equal to omega. Right? If k dot v is really far from omega, it can't really interact with the wave. So it'll just go shoot through the wave, and the interaction will be averaged out. And so you won't really, the particle can't kind of pick up kinetic energy from the wave. And so what's happening is that for the macroscopic plasma wave to interact with the kinetic part of the plasma, it only interacts with the particles who have k dot v approximately omega. But if k is really small, then that means you're looking at really, really high velocities. So you're really looking at the high velocity tail of F naught. And in fact, the decay rate is completely dictated by the tail. So Benoit has an explicit expression, which you can guess, but it's not that obvious how to prove, which basically says that the Landau damping rate lambda can be exactly related to basically the radial, in the case when the background distribution is radially symmetric, you can get to the lambda is exactly like the radial derivative of F naught times like R squared or something. So it's like an exact formula. And so, for example, in their work, so Alex Ionescu, Benoit Pauseter, Shuisheng Wang, and Klaus Widmeyer, they have a work that studied the problem with this Poisson distribution. And there, the Landau damping rate is really relatively fast, so it's almost like kinetic free it's almost like kinetic free transport again, where the lambda is like k. This paper is still very hard and subtle. They're doing the nonlinear problem in this paper, and I'll talk a little bit about that in a bit. Yeah, anyway, so that's what this wave particle resonance is happening. So actually, when you study the problem on R3, as we as a community go to more and more generalized setups, this wave particle resonance is exactly going to be relevant, is going to be very relevant, and it's based on the interaction of the kinetic equations with the macroscopic regime. Okay, I'm going to skip the discussion of collisions. It's interesting, but it's a little bit of an aside, so let me just skip that. Let's talk about nonlinear problems again for Vlasov. So a really obvious question is, does this survive nonlinear perturbation? Because there's no like dissipative part or anything like that. This Landau damping is not damping, it's like a dispersive effect kind of, but it's not that either. It's just, it's its own thing. It's a mixing effect. So one early answer to this question, does it survive nonlinear perturbation? One early answer was no, depending on how you phrase the question. So there was a result by Lin and Zhang on Vlasov Poisson on the circle, so just on T. Well, T cross R, of course, so X is on T. And what they proved is that if you look in low enough topologies, there are X-dependent equilibria, which are arbitrarily close to the homogeneous equilibrium. So of course, those solutions obviously don't damp. They're just sitting there forever. They're examples of what are called BGK waves. So it's interesting. So that means like in L2, there are completely nonlinear, non-mixing solutions arbitrarily close to equilibrium. So these, in dispersive equations, this would be called a small soliton problem. And you might think, okay, well, let's just start with my initial data in H a trillion, and therefore these guys are far away from, you can prove these guys are far away from equilibrium in H a trillion. But that doesn't really work because the solutions actually are, the PDE is unstable in H a million. So the homogeneous equilibria are definitely unstable in H a million. They're unstable in all HS with S positive. And so that doesn't really help you unless, you know, a priori, that doesn't help you at all, I would say. So that doesn't solve the small solid time problem. It actually gets much worse. So this isn't that big. I mean, this isn't a direct issue, so to speak, in the proof. What is a direct issue is the following observation. So let's just think about kinetic free transport. So again, back to the simple kinetic free transport, forget about all this Landau damping stuff, just the particles just moving with fixed velocity. Now imagine that you choose your initial condition to be concentrated at some frequencies k0 and eta 0. So x wave number k0 and v number eta 0. And eta 0 is way, way, way bigger than k0. Then your distribution function in Fourier is going to look something like this. And you know, the particles are going to be basically equally distributed along the ring, so you won't see any density fluctuations at time 0. Right, so like, what is Landau damping? Landau damping is basically the following. You have a ring and you put particles on the ring. And if you put all the particles, initially, if you put all the particles in one spot, but with different velocities, when you start time forward, the particles will approximately equidistribute around the ring for most of the time. So Landau damping is just the infinite particle limit of this very simple observation. That's it. That's all that you're seeing in this mixing effect. And so let's say we start the sort of particles sort of approximately equidistributed around the ring, but in some specific manner, such that as time goes forward, instead of mixing in phase space, they're actually going to unmix in phase space. And so the density fluctuation will actually increase as a function of time, and then it will reach its maximum at what's called a critical time. So time eta 0 over k 0 is the critical time. And at that point, the density fluctuation will be its maximum. And then as you run time forward, the density fluctuation decays and remixes. This isn't weird. This is like, you know, take the wave equation on R3. This is a time reversible equation. And if you start with initial data, which is localized, you know that it decays in L infinity to like 1 over t, whatever. But of course, if you just time reverse a dispersing solution, what really happens is that, you know, small waves that are at infinity come in, focus at the origin, create a large response at time equals 0, and then continues through the origin and disperses again. So anytime you have a decay in a time reversible system, something like this has to happen. So that's all that is. This sort of transient growth and decay mechanism was first noticed in fluid mechanics by Orr in 1907. As far as I know, it doesn't have a name in plasma physics, but it's the Orr mechanism in fluid mechanics. And actually, you can think of solutions of the kinetic free transport equation as a superposition of these waves. So every wave is just tilting like this, and you're going to construct your solution by just looking at your solution as a superposition of these waves. That's a reasonable way of thinking about the kinetic free transport. And so what can happen is that, well, once you turn on the nonlinearity, the superposition of waves can interact with each other, and you can form what's called an echo. So the physicists knew this was going to happen almost immediately. So it was only 4 years after they captured Landau damping in the laboratory that they did these experiments. And so this is the electrostatic energy on the y-axis and time on the x-axis. So what happens is at time 0, they poke the plasma at sort of scale 1, and then the plasma Landau damps sort of rapidly. And these wiggles are due to the Langmuir oscillations. Then they poke the plasma again at this future time. And so there's just, you know, pokes the plasma and then it Landau damps. And then the plasma spontaneously makes a response at some future time. So the electric field was 0 for a while, and then the electric field suddenly becomes large again and then decays again. So this is why it's called an echo. And you can actually chain the echoes, so you can have a bunch of different echoes come off. You know, you can make like 10, 20, I don't know how many they can do in a laboratory, but maybe 6, I think. So what's happening? So there's a nonlinear interaction between, so to leading order, the solution is a superposition of these waves, but all at different places in their evolution. So when they poke the plasma the first time, they put energy in a wave like, you know, in this wave, and then that, not energy, but information, let's say. And then that wave damps, right? So that wave mixes and goes to high frequencies in velocity like this. And then then they poke the plasma again at a wave that's sort of at macroscopic scales. But then there's a nonlinear interaction between the macroscopic scale and the scale that was added originally. So there's a nonlinear interaction, two-wave interaction, and it puts and excites this mode here, some mode over there. And then that mode then unmixes, goes through its critical time, and you can see the response. And you can chain these echoes. So the first echo kicks off the next echo, kicks off the next echo, kicks off the next echo. So how do we see that in the equation? So you can actually see this clearly is a strong term, but you can see this in the equations. So if you go back to the Voltaire equation and then you leave the nonlinearity in, when you look at the density, this is what the nonlinearity turns out to be. Okay, it's a calculation. It's not a hard calculation actually. It's just you just have to keep doing it. And so this is how the nonlinearity appears in the Voltaire equation. So you get a piece from the initial data, you get this nonlinear piece, and then you have the sort of linear interaction term also. But that's whatever, we know how to handle it. If you think about this guy, so this is the distribution function. That distribution function, that's not smooth, because if you think that you're close to being linear dynamics, it should look like more like a solution of free transport. So this distribution function should look like this. This look like a solution of free transport, where this G is kind of uniformly bounded in HS. That's the idea. That's what you think should be happening if you really are close to the linear dynamics. And so if you put this oscillatory phase in here and fiddle around, you can basically see that this oscillatory phase is going to highlight interactions where KT is like L tau, and everything else is kind of irrelevant due to the regularity of G. And you get a toy model that looks like this. So what it tells you is that the density at time tk is strongly affected by the density at time sort of t equals L, sort of tau equals K divided by tau equals KT divided by L, assuming K and L are integers. And so actually, if you think also about regularity of G in K, you can see that the largest effect should be when L is like K plus 1. So rho of TK is strongly forced by rho of KT divided by K plus 1 comma K plus 1. This is actually a plasma echo. And if you think about it, what's happening is that there's cascades. So K plus 1 forces K, which forces K minus 1, forces K minus 2. So it's a high to low frequency cascade in X. So the X waves are always decreasing frequency as you chain the echoes. It's a bit hard to see, but if you fiddle around, if you think about everything on this function G, this free transport profile G, you can actually see that this cascade is actually a low to high frequency cascade in G, and it all happens at the same frequency. That's not obvious, so you have to fiddle around with this for a little bit. But if you do that, you can see that if you count over all of the possible plasma echoes, you can actually derive a kind of amplification factor like this. So this amplification factor is about 1. That's sort of the weakest amplification factor. And this amplification factor is the largest, and you get all of the wave numbers in between. And if you count over this, you see, okay, well, this looks like kind of epsilon eta to the nth power divided by n factorial cubed, where n is this number. And so if you fiddle around with that, you get this explosive growth. So it's like e to the epsilon eta to the 1/3. And so what this tells you is that if you want G to be uniformly bounded in your some regularity class, you need to allow this kind of like sub-exponential, but faster than any polynomial explosion. So that led, so Clément-Moreau and Cedric Villani, they conjectured that this S equals 1/3, that that's 1/3 regularity in this exponent is kind of sharp for proving Landau damping. And so what they were able to prove on the torus is that you do have that the nonlinear problem does Landau damp as the linear problem predicts if you have enough regularity. So they got analytic and a little bit below analytic. So they have like this exponent S close to 1. Then Clément and Nader and I, we came up with a pretty different proof, which is much simpler, where we got the sharp S bigger than 1/3 exponent. And then there's another proof which sort of streamlines some of our inefficiencies. So we made a few inefficient choices in our proof, and they streamlined it a little bit further. So now I think you can write an entire self-contained proof using nothing but basic Fourier analysis in maybe basic Fourier analysis and Laplace transform, maybe 15, 20 pages or something. Like now you can really have an efficient proof. So basically what the statement is the following. If you start with data which is smooth enough, again, S needs to be bigger than a third, then you get the, let's just look at this one. Then you get the Landau damping. This V should not be here, it's a typo. Then you get the Landau damping as Landau would have predicted. And then this gives you this nonlinear, this gives you the scattering result. So that's not so interesting. So the important thing is this super fast decay of the density. Again, this is on a torus, of course. And actually in dimension equals 1, you can actually prove that this theorem is true with S equals a third and lambda to be approximately epsilon to the 1/3. And so you can kind of prove an analog of this theorem, which shows you that this super high regularity requirement is only for frequencies that are also themselves super high relative to epsilon. Right? They have to be 1/epsilon. The frequencies where you really need this strong decay is like 1/epsilon, where epsilon is the size of the data. The other, and that is a very hard theorem. No, relatively hard theorem. What is a relatively easy theorem is to show if you have kind of like H10 regularity, then you can prove this theorem up to time scale 1/epsilon. So you can prove that the nonlinear dynamics don't start dominating potentially until time scale 1/epsilon. It turns out that that's essentially sharp. So here's a result of mine from 2016, which says, okay, I can come up with one example on the circle. So I have one background distribution such that if I choose any number of derivatives that I want to lose, then no matter how big, no matter how many derivatives I decide I'm going to start with, no matter how many derivatives I decide I'm going to be small with respect to, I can always make my profile lose that arbitrary amount of derivatives. And in particular, I can make my electric field deviate from the linear prediction by that many powers of time. And this time scale is basically a log epsilon past the 1/epsilon time scale. That's what I mean. So 1/epsilon is basically sharp. You can't really go further than this and expect linear dynamics. And the statement of the theorem is less than you want. So first of all, you want S equals a third. And in the electrostatic interaction, I do need to make this delta to be kind of small. I can't make it sort of 1/100. For gravitational interactions, you can make this delta independent of epsilon. And then if you remove the requirement that the initial data should be strictly positive, and if you just remove this F0 and ask the question about Vlasov without the F0, then I can prove the theorem that you want to be true, or a theorem that's kind of closer to what you want to be true, that you get this kind of norm explosion result in Gevrey regularities for everything less than a third. That I can do, but it's not physical, so I didn't pursue it carefully. So the point is that the result shows at least that you get log epsilon little plasma echoes chained one after another. So the construction is basically to construct a bunch of plasma echoes directly. So you can show basically that the solution in between the critical times, the solution is the density is exponentially small, and then in epsilon, and then at the critical times it's like epsilon to some power. So you have a sort of big difference between the echoes and the not echoes, and it just, yeah, you just see log epsilon little echoes. I think, is this supposed to be a 45-minute talk?
I think it's a 1-hour talk as far as I've been told. I might confirm.
Well, yeah, it's
By the way, I don't want,
basically
yeah.
55 minutes. I mean, sometimes.
Okay, so I don't want to. Right. Let me just give a really brief summary of the proof rather than trying to go into as many details as maybe I would want to.
Jacob, I think you've done about 35 minutes, so you're not at the end of your time yet. No panic.
Okay, all right. I still don't want to hit people over the head with a detail hammer, but yes. So here's how the construction works. So you want to, it starts simple. You say, okay, well, I want to basically come up with a kind of asymptotic expansion of my solution. So I'm going to have a low frequency approximate solution. And roughly speaking, I'm just going to put in the solution to free transport. I'm specifically choosing these profiles very carefully so that essentially when you start taking Fourier transforms, the formulas become explicit. That's important for the proof. And so I'll take a low frequency approximate solution, and that's essentially the linear dynamics. Okay, so you can actually use the true linear evolution for FL instead of the free transport evolution, for example. I think that's actually what I do. I think I use the true linear evolution for the low frequency approximate solution. And then the high frequency approximate solution, what I want to do is I want to relinearize the equation around, instead of F naught, I'm going to relinearize around F naught plus FL. So it's like the second iterate. But that equation is ugly, and I didn't know how to work with that equation. So I'm not actually going to do that. I'm going to solve something that's close to the linearized Vlasov equation. So it's not actually the second iterate. It's something that's like the second iterate. So it's this form. And I'll explain why it's like that form on the next slide. So everything I've sort of removed by this free transport action. And I'm going to start the initial condition to be what Orr said I should start it with. Basically, I'm going to take exactly what Orr said. I'm going to take an initial condition, which is concentrated at some frequency eta naught and some frequency k naught, where eta naught is huge and k naught is not that big. So k naught is basically log epsilon to the 1/3 power. And eta naught is like 1 over epsilon. The real proof is constructed differently. You sort of time reverse something. It doesn't matter. I mean, it matters a lot for the proof, but it doesn't matter for your heuristic understanding. So the high frequency construction is done so that the high frequency approximation, the high frequency density actually exactly solves a Voltaire equation. And it exactly solves this explicit Voltaire equation. And that makes things relatively easy. So once you have something like this, you cannot solve this. Well, I cannot solve this explicitly, but I can almost solve it explicitly. You can use back substitution. It's basically like inverting a nilpotent matrix, or like an upper right triangular matrix. So you can almost invert it explicitly. It's the presence of this linear term is what makes it complicated, actually. So if that wasn't there, it would actually be easier. But you can still do it. Yeah, the point is that you need to get upper and lower bounds. Then the hard part of the proof is actually proving that the error remains small enough so that the errors in G, so G is like the error that you made with this approximation, don't swamp the high frequencies of FH. So you need to control the regularity of G really precisely. The problem with that is that G is also going to get hit with this echo phenomenon. So there's going to be, like, G will also have its high frequencies exploding, but it will be in general worse a priori because you don't know anything about G, whereas FH you know precisely. And so to make this work, there's a lot of tricks. One of the tricks you need is to use very precise norms that shed regularity as a function of time and frequency in a very specific way. So this was based, building on an idea of that Netter and I used in the fluid mechanics to solve kind of a related problem in fluid mechanics. But then porting over kinetic theory has some differences and things like that. Then so use some really crazy norm that sheds regularity at the critical times based on what you think the plasma echo should be doing. So that's how you keep track of G almost as well as you keep track of the approximate solution. Yeah, is a lot of work that goes into it, but that's basically how it's done. Okay, I'm not going to talk about how collisions. Okay, the one thing I want to say with this slide is this nice little kind of end point, which is that in the physics literature, they were always debating about whether or not you should see Landau damping in the nonlinear Vlasov-Poisson equations, for example, at least on the torus. And you have some physics references that says, yes, you should. Some physics references that say you should only see it until time scale 1 over epsilon. Some physics references that say you should only see it because of collisions. So that the real Vlasov equations, you shouldn't see it in the real Vlasov equations. You should only see it in if you include collisions. And the interesting thing is that all of these were correct in a certain sense. So it all depends on what regularity class you're willing to work in. So if you only want to work in HS, then you may not see nonlinear Landau damping. You may only see it at the time scale 1 over epsilon, but you can also see it with collisions in HS. But if you work in Chevret class, you can see it without collisions. So all these physicists were actually correct, and they all had good intuition. So they were all correct, and they all had good intuition for why. Okay, so on R3, you can prove basically you can prove this theorem in HS on R3. So you can prove the correct analog on R3. Sorry, if you have screening. Okay. And so we first proved this using a very Eulerian proof. So it was very much like an extension of our proof on the torus to R3. Then this other team came up with a proof which is somehow very Lagrangian, actually like earlier work of Bedrossian de Gon, which is the case where you have no background. Yeah, anyway, both proofs work. If you want to get the full statement of the Landau damping where you gain a time decay for every derivative, then you need to put the two papers together. But this first paper showed that you can actually close dispersive estimates. You get this kind of estimate, and that closes at the nonlinear level. You don't need Landau damping to close the arguments. The way our version of the proof works is an observation about the plasma echoes, which is that plasma echoes, first of all, in order to really have a problem, you need to chain these resonances. And so these are when KT, in the Voltaire equation, these are when KT equals L tau, or approximately equal to L tau. And if you want to make a chain of these, that means you need all of the wave numbers to be collinear, because T and tau are obviously scalars. And so the intuition for why the plasma echoes sort of are a problem on the torus, but not a problem on R3, is that the set of collinear frequencies is codimension 2 in R3, whereas on the lattice, they're a positive measure set. And so, if the dimension is high enough, turns out 3 is high enough, then the plasma echoes are extremely weak. I think actually earlier this year, someone proved a version of this theorem with dimension equals 2, which is kind of like the critical case, where you think it should be true, but it's not clear how to close it. Then there's a beautiful paper that came out earlier this year that is able to handle the case of R3, again in HS regularity, for unscreened, so plasma electron waves. So you really have no screening. So really the Vlasov equations, but you have a really thick tail so that you have a lot of extra Landau damping on the Langmuir waves. This paper is quite sophisticated, it's really interesting. So even though you have a lot more Landau damping than you would get if you have a Maxwellian background, it's still a very non-trivial theorem to prove the analog of this theorem. Okay. So what do we still have to do? Well, lots of things. So first of all, there's a lot of things I did not talk about. So one thing that I didn't talk about was, for example, what happens when you add magnetic fields. So there's a couple of versions of this. So first of all, we mainly only know some linear results. So for example, if you do Vlasov-Poisson with an external magnetic field in the torus, then there are waves that do not damp. These are called Bernstein waves in kinetic theory. And so you do not have Landau damping, or there are waves that just don't damp. Similarly, if you study relativistic Vlasov-Maxwell, so now you include a self-generated magnetic field, but you don't include an external magnetic field, you still get waves that don't damp. So you have light waves that are propagating through the plasma, and they just don't damp, basically. Literally, they do not damp. And so one of the things we don't understand really is we don't have results for nonlinear results when you have these weakly damped or completely undamped plasma waves moving through your plasma. So that is still basically completely open. This recent result of Alex Ionescu and Benoit and them, that's the closest thing we have so far, this result. The other thing we don't really understand is this, I have this example of plasma echoes, and even though I found the proof pretty hard, it's a little bit of an underwhelming result. It's not exactly like, you don't prove that it doesn't Landau damp. You don't really characterize the dynamics as time goes to infinity. It's a norm explosion result. It's a norm inflation result. So it's basically just saying your dynamics are very nonlinear, but I don't know, maybe if you wait long enough, they become linear again, or or whatever. Maybe it completely transitions to some completely craziness, or maybe it doesn't. Maybe you have modified scattering. I have no idea. Nobody has any idea. So we really don't know what happens for general initial data on the torus. So that's kind of a really open question. Another thing that we don't know much about yet is this kind of macroscopic limit that you see in the linear equations. You're starting to see, and I think this is a general principle. It's a little hard to write down rigorously, for other cases, though I started to do so, but it was such a mess. But essentially, anytime you have a kinetic theory model, no matter how you set it up, if you have an external magnetic field, a relative plasma Maxwell, or whatever, anytime you take a macroscopic limit, you look at long waves, you're going to see basically Euler-Maxwell waves. So the entire plasma dispersion relation that you look at in a plasma wave book, you know, with all of the X waves and the O waves and blah, blah. You're going to see all of that stuff in the macroscopic limit. And so it's actually an interesting question. What really are the leading order kinetic corrections to these macroscopic models that you can see when you zoom out of the kinetic equations? This is really important in physics. Physicists debate these kinetic corrections, and I don't think there's any clear consensus. Okay, anyway, I could list a bunch of other open problems, but they're just increasingly impossible. So I'll just end there. Okay, thanks everyone.
Thanks, Jacob. I'm trying to get back to all the videos. So I'm doing the clapping for everyone. So we have time for a few questions. So please either unmute yourself. Well, maybe raise your hand first, and then I say who can speak. Otherwise, several people could speak at the same time, or put your questions in the chat. Okay. Yeah, Elgo. Yeah, go ahead, Elgo. Unmute yourself.
Thank you very much for the very lovely talk. I mean, just wondering for the very last part you described for the magnetic case that basically hardly anything nonlinear is known.
Mm-hmm.
I was wondering, even in this case where you would have some kind of collisions, whether you could, I mean, because if you have collisions, you can swamp away lots of the difficulty, I have a general feeling, whether you can say anything.
Well, it depends what you mean by swamp away the difficulty. So, you know, when you add collisions, you really want to get some kind of like stability threshold type results that are good. So of course, like if you don't care about getting a good stability threshold, then you can prove that you have stability with collisions. So we at least did this for. So I have a paper with Fei Wang. We at least did this for Vlasov, Fokker, Planck linearized in the periodic box, and you know it's stable. And I'm sure that if you put enough derivatives and you made the initial data like kappa to the 12th power or something, you could very easily prove global stability. But I mean, I don't know if that's so enlightening. You know what I mean? But so getting sharp results, getting really characterization of what should really be happening, I think it would be pretty hard.
Yeah, I just was wondering if they could already make some kind of partial progress that you kind of somehow beat the very trivial bound by a little bit.
Yeah, I mean, actually, even beating the trivial bound, which would be like size like kappa, wouldn't necessarily be that easy with an external magnetic field. That's a worthy. I would assign that to a graduate student, for example, a good graduate student. It's a worthy endeavor. Even getting that bound is not that obvious to me. Hopefully, I mean, okay, but the thing is, you could definitely succeed, because if you can't do it with kappa, I'm sure you could do it like kappa squared or something. So I would be comfortable giving that question like that to a graduate student, but I wouldn't necessarily expect them to find the sharp answer. And I'm not sure. I don't know. I don't claim to even know the sharp answer. And it may depend a lot on how you phrase the question. Details of like, do you want to know the nonlinear dynamics or not, or something that's it may be subtle how you phrase the question. Because we know in fluid mechanics, for example, like the 2D Couette flow in fluid mechanics, in 2D, if you have no boundaries, then it's kind of uniformly stable in L2, regardless of regardless of a small parameter like the analog of kappa. It's stable, but you can't prove anything like, does it have the analog of Landau damping and the enhanced dissipation effects? You don't know that that's true unless you take data which is either super smooth or much smaller as a function of nu. So you have stability kind of trivially with like a one-line proof, but you don't know what the dynamics are unless you put more restrictions on. So you know what I mean? It really depends on how you ask the question.
Okay, I don't see any.
Thank you.
Other hands or in the chat. Okay, I might ask a question. question to give time for other people to think. So Jacob, one thing I've been wondering, and it's a good time here because you have this overview. So maybe you can tell me whether it would fit the different pieces of your overview, a whole in the overview for. So this paper of Ionescu, Posader, Wang, and Widmeyer is really nice and intriguing. I mean, I'm like you. You spoke about it several times. I agree. This paper is really nice.
It's really cool, yeah.
And by taking a very particular, well-chosen. So you're right. It's a well-chosen stationary solution because of the thick tail. But it's also in the paper. It also seems nice because it lends itself to a particularly easier Laplace Fourier analysis at some point in the paper.
Yeah, that's right.
But you're
you
right.
can more easily explicitly solve for the, like, you don't have to, like, doing the analog of our paper is just
much simpler.
Much simpler, yeah.
Yeah. But that could be just technical. The key point, as you say, is the thick tail. But I was wondering,
somewhere
now if we go back to the confined setting, what do you think about the following question? And is your paper about the chain of echoes providing any obstruction or not? Could there be a particular well-chosen F0 or V solutions in the confined setting for which the regularity threshold for the stability be lower?
I don't think so.
Lower than the
yeah.
Okay.
I personally I don't think so, but I don't have a proof of this. So in some sense, this theorem is about this particular F naught, and this particular F naught, which I scribbled out, is the same. It's kind of like the same thing that they're using in their paper, because this is the one F naught that you can explicitly solve the linearized Vlasov equations. You just literally just write down a closed form solution. Doesn't have any stupid contour integrals or estimates or anything. It's just this is the answer.
Because in your paper, remind me, it was 1D in V because it's enough to see the mechanism. It's 1D in V, so your dimension plus 1 in terms of integrability, which is the same as what they do 3D, and they have
exactly.
Right?
So it's the same thing. So like, you know, because it's like when you take the Laplace transform, you do like marginals, and then take the Fourier transform and stuff. Like, you know, like you guys described it in your paper pretty clearly. And so their background distribution is the analog, sort of the n-dimensional analog of this background distribution. So this is the only class of background distributions that you can solve explicitly. So the Maxwellian case, you don't have an explicit solution to the Vlasov-Poisson equations. It's more complicated. I don't think that it matters because they all should have the same general, like, Langmuir oscillation plus decay. And I don't think it matters, but that's just a conjecture. I don't really know what happens.
Okay, yeah, but at least, your point is quite convincing that it's probably not, at least in this direction, that there could be, it's not in the same direction as what they did, and in R3 that
probably not.
Could be,
I would really
conjecture
that that
something else, but it would not be related to the thick tail like that. Okay.
Yeah, that's what I would say.